Okay, this is the third Taylor polynomial example problem. Just like the previous two, what we want to do is we're given this function here, x to the 2/3. We're going to start by finding its nth degree Taylor polynomial, but now instead of the first two problems, we had n is equal to 2. Now we have n is equal to 3. So we want to find the third degree Taylor polynomial of this function centered at 1. And then we're going to use Taylor's inequality to get an estimate on the maximum possible error that we would get if we used that Taylor polynomial to approximate the function, assuming that the x values that we would input are restricted to this range here. What's the maximum possible error based on Taylor's inequality? And then at the end, we're going to graph the actual error by just doing a graph of the function, then subtract from that the Taylor polynomial and compare that to what Taylor's inequality gave us. So, okay, first let's get the Taylor polynomial. So remember, what we're doing here is we want to get t sub 3 of this function, right? Now, it's a little confusing because when you think about traditional partial sums, the S sub n, it's like you think about you're summing the first 3 terms of the series, which in this case would be the Taylor series. But it's different with Taylor polynomials. This 3, that can be the case where we're summing the first 3 terms, but really the n is about the order of the polynomial. It's not about the number of terms you have in the polynomial. It's about the order. So we're going to be going up to the x cubed term, the x minus 1 cubed term. That's what t sub 3 means. So, okay, to do this, we start by just going through the same process that we would do if we were making the actual Taylor series. So we've got 2 columns. On the left column here, we're going to write the function and its derivatives. So x to the 2/3. All right, now f prime of x to the 2/3 x, 2/3 minus 1, 2/3 minus 3 over 3 is minus 1/3. Okay, so that's okay. All right, now f double prime minus 1/3 times 2/3 is minus 2/9. X to the minus 1/3 minus 1, minus 1/3 minus 3 over 3 is minus 4/3. Okay, now so we've got let's see, x to the 4th, the cube root of x to the 4th. And we can actually simplify this a little bit more. So this is going to be x cubed root of x, right? Because this is x cubed times x. Okay, now the second derivative is all we need to get to the, well, oh, no, we're going to n is equal to 3 this time. So, okay, so we need to go to the third derivative. Okay, so we've got minus 4/3 times minus 2/9 is 8/27. X to the minus 4/3 minus 1 minus 4/3 minus 3 over 3 is minus 7/3. So let me do this, actually. Let me... Okay, I want to make some room. Okay, so this is 27, and then x to the 7th. Okay, now this is x cubed times x cubed times x. So we're going to get okay. Okay, now, so this is enough to get the up to the third, the x minus a cubed term. However, we want to go one more derivative because we're going to be using the Taylor inequality, right? So, okay, let's see. 7/3 minus 7/3 times 8 over 27. So 27 times 3 is 81. Okay, 8 times 7 is 56. Okay, minus 7/3 minus 3 over 3 is minus 10/3. Okay, x to the 10th, that's, we could take it an x cubed, so that's going to be 81x cubed, cube root of x, and then minus 56. Okay. So now we want to come to the right hand side column and plug in the center point. So, okay, 1 here, 2/3. Okay. And we're not going to need to plug anything in for the fourth derivative. So, okay. All right, now we don't need to find any pattern or anything like we would for the Taylor series because we're just taking the first these first four terms. So okay, now so the C sub n, we know for the Taylor series, is the nth derivative evaluated at the center point over n factorial. So let's write out the C sub n for each of these. So this is, because this is f, this is, right, where a is 1. So the C sub n, we just divide by n factorial. So here we divide by 0 factorial. This is the 0th derivative. So this is 1. Here we divide by 1 factorial, 2/3. Here we divide by 2 factorial. So this is minus 1/9. Here we divide by 3 factorial. So we're dividing by, it's divided by 6. So 8 divided by 2 is 4. 6 divided by 2 is 3. So 4 over 81. Okay, so now we've got the coefficients for the first four terms of the Taylor polynomial, but this is still t sub 3, not t sub 4. Why is that? Because we're going to be going up to x minus 1 cubed. So, okay, we've got 1 times x minus 1 to the 0 power, so it's just 1, plus 2/3 times x minus 1 to the first power, minus 2/9 times x minus 1 squared, plus, or no, it's, no, 1/9, minus 1/9. Okay, plus 4 over 81 times x minus 1 cubed, right? So t sub 3, we go up to the third order. Okay, so what is this? This is an approximation for x to the 2/3 power. This is f of x. Right? So if we're, the idea is we could plug in any value we want, any x we want technically, but, well, actually not with this restriction we can't, but like in general we can, but the idea is if we're near the center point, if we're near 1 and we plug that in here, we're going to get something that's close to what you would get if you plug that same value that's near 1 into the actual function. That's the idea. Okay, so now let's get, and What is the maximum if we're going to input anything on this interval? That's the restriction. You can input any x you want as long as it's on this interval. Then what is the maximum possible error you could possibly get? Error meaning the largest possible difference, positive or negative, the absolute value between if you plugged in that value into the actual function and what you got with what you got there, and then what you got with the Taylor polynomial. Okay, we're going to do this using we're going to do this using Taylor's inequality. Okay, so Taylor's inequality it's all about finding this capital M. Once you have the capital M, then you're done, because this is Taylor's inequality. We're trying to get the absolute value of r sub n of x. That's what we're trying to get. We have n, we picked n. We have a, we pick a. We have d here. D is just based on, so you can see d is 0.2. We're plus or minus 0.2 from 1. So we just need m, capital M. So what is capital M? How do we get it? Well, they tell us here, it's this here. So we need the n plus 1th derivative to get capital M. Okay, well, because, all right, well, we're trying to get r sub n of x. Well, what specifically are we trying to get? What n, right? What r are we trying to get? Well, we know that it's, so the Taylor series, which is equal to the function. This is the full Taylor series, going to the infinite sum. That's equal to what we're doing, t sub 3 of x plus r sub 3 of x. We want r sub 3. That's what we have, t sub 3. If we can get an estimate on the size of r sub 3, that's going to give us the error. So we need and just to point out, this does get a little bit confusing if we have 0 terms. So remember with the infinite series, sine x, cosine x, every other term was like a 0 term. If that happens, then I talked about in the textbook section, it gets a little confusing on what r we're using. For these initial problems, we're focusing on simpler cases where every term was non-zero. So we want r sub 4. R sub 4. So, or no, r sub 3. I'm sorry, r sub 3. So that means that we want to look at the 4th derivative. So what is the 4th derivative of the function? Okay, well, that's this here, minus 56 over 81 x cubed, cube root of x. And we can actually take that absolute value. So we can take that negative out of there. But we still need the absolute value, because, this could still be negative, right? Depending on the x you put. So, okay, this is, well, m is this function here, the absolute value of this function here. Is there some number, capital M, where if x is between, so we've got for x minus 1 is less than or equal to, we see it's 0.2. These two mean the exact same thing. These are two ways of writing the interval, the x restriction. Okay, for any x that you plug in, that's within 0.8 to 1.2. For any x you plug in, is there one value that, no matter what x you plug in, the value of the function is greater than or equal to all the other values? Well, yeah, pretty much any function that behaves normally, like, this is a continuous function, at least other than at x equals 0. Yeah, there's going to be a number there's going to be a maximum, right? It doesn't have to be like only one value. You could have all this, if this is from 0.8 to 1.2, you could have a like this. Well, still, that's fine. Whatever this corresponds to, that's the capital M, because there's nothing that's greater than that value. Or, like a regular function, it could just be whatever. There it is. There's capital M, whatever that corresponds to. Just find the maximum value on the interval. It's like the extreme value theorem problem, right? Well, we see here it's just what's the smallest value of x. That's going to be the biggest. That's where this is going to be the biggest. That's 0.8. So M is equal to, we just want to plug in, so 0.8 cubed times 0.8 to the 1/3 times 81, 56 divided by that, 1.45458. That's capital M, right? As far as the absolute value of this, it doesn't matter. This is, on this interval, we're never going to get a negative value anyway, so we could have just removed the absolute value anyway once we specified the interval. Okay, so we've got capital M. So now we have everything we need. R sub 2 is going to be less than or equal to, so n plus 1 factorial, that's 3 times 2 is 6. Okay, x minus 1 to the n plus 1. No, this is not right. I'm sorry. We want r sub 3. So 3 plus 1 is 4 factorial. That's 24. Okay, x minus 1 to the 4th. Okay, and this is, so okay, this is equal to that divided by 24.060607. Okay, for, once again, you want to specify that because that the capital M is based on this restriction, right? So, okay, we've got, there it is. Okay, now we're not done yet because it depends on which value of x we pick, right? The distance of the Taylor polynomial from the actual function value is going to depend on the x we pick. So let's pick the x that makes this the largest. Now you might say, well, wait, didn't we choose the x over here already? That was a different, we were just using that to find what M was. Once we have M, now this is different. Now we've got R sub n, there it is, R sub 3. Okay, so the way we're looking at it is, no matter what x we plug in to T sub 3, what's the largest possible error we could get? Well, okay, that's going to be, this is the absolute value, and we saw that there's the farthest we can get away from the center point. So just looking at this, when you get to this step, this is always going to be at the endpoints every time because it's just the x minus a. So you're just going to pick an endpoint here, but it might not be the case that for the capital M that the endpoint results in the capital M value, giving you the capital M value. So you might get one of the middle points gives you the M value, but that doesn't matter. That doesn't mean you have to plug in that value of x here. You're going to plug in the endpoint. So this is going to be 0.2 to the 4th. So okay, 0.2 to the 4th times this, 0.00097. Okay, and there we go. There it is. It doesn't, we don't have to plug in something for x here. This is it. This is we have T sub 3 of x, and we're trying to give you have the infinite series, which is the function, is equal to T sub 3 of x plus R sub 3 of x. For you could plug in any x value you want into here that's within 0.8 to 1.2 to this here. What is the, for any of those x values, what's the largest this could possibly be? There it is. Okay, now let's go ahead and graph the actual r sub 3 of x. That is equal to what? We know it's the absolute value of the function minus and all of this. So I'm just going to put, right? I can plug this into Desmos, x to the 2/3 minus all of this. So let's graph that and see what the actual maximum error is. And you might say, well, why wouldn't we just, what's the point of Taylor's inequality if we can just do this? These example problems are just for illustration. Yeah, if you could easily just do the graph like this, and then yeah, of course, that's what you do. Why would you use Taylor's inequality? But it might be the case where it's difficult to do this, or maybe you actually don't have the actual function. There could be different reasons. So, okay, there is r sub 3 of x, the absolute value. And so, okay, we go from 0.8 to 1.2. So there. Looks like the 0.8 side is a little bit higher, so the maximum is a little bit above 0.00005. So this is not bad, right? That was about 0.00005. Here's 0.00097.